pick an element or a compound. We're going to draw an MO theory for a diatomic molecule, but I don't want to know what that element is. But try to pick something between boron and neon. Okay? Tell me when you have agreed to something. But don't tell me, because I'm going to read their mind and solve this problem without knowing what it is. That's how easy this work MO theory is. And I'll just call it E2. Okay, do you have a molecule? Okay, and does it have a charge? Okay, okay. And it should have a charge like really bigger than +2 or -2. It should not. Okay, because that would be ridiculous. All right. So what you're going to do to draw the MO theory, we'll just generate it for an unknown molecule. Those three in the front, I think 3 people, know the answer. I do not. It doesn't matter, as you'll see. Okay, so what you do is you have the molecular orbitals in the middle and the atomic orbitals on the outside. Okay, so 2 atoms called E fly together to make a diatomic. On the exam, on the final, you're going to have a diatomic and it'll be homonuclear, meaning both of the same atoms. Okay? All right, so the atomic orbitals on the outside, molecular orbitals on the inside. You don't need to draw core electrons. Those electrons in this case would be called what? Or what orbitals would they come from? A 1s orbital. So you don't have to draw the 1s molecular orbitals unless you really feel like it. So all you would need to do is draw the 2s and the 2p. How many lines am I going to draw here? 3, because each p orbital for a given n, in this case n is 2, has 3 orbitals, a px, a py, pz. Okay, so the same thing over here because it's the same atom on this side, so a 2p and a 2s. Okay? Again, I'm just drawing not the core electrons, but the valence, just the valence. All right. So every bond has how many parts? 2. They are called bonding and anti-bonding. So every time you're generating a bond, you better have 2. Okay, for each atomic orbital that you have. So bonding is always lower energy, and an anti-bonding is up here higher energy. And we beautify this by putting these little kind of dots or dashes to show where the middle ones, the molecular orbitals, come from. In this case, they're coming from the atomic orbitals of 2s, so we draw the dashes from the 2s. All right. These form what kind of bonds? Sigma. Both of them are called sigma. The one higher up in energy has a star representing the anti-bonding. The one lower energy doesn't have a star because it's bonding. And then the subscript, just a 2s, because it came from a 2s orbital. So the subscript is always the orbital it just came from. All right, and now that's the bottom half. Let's see the top half. The top half's a little more interesting because we have 6 atomic orbitals. So we're going to have 3 bonding and 3 anti-bonding. Each has 2 parts. Okay? So, people who picked it, you need to tell me, did you pick oxygen or higher in atomic number, or did you pick nitrogen or lower in atomic number? Nitrogen or lower. So, just from knowing that, I already know the pattern for the 2p orbitals. It must be 2, 1, 2, 1. Okay? Because nitrogen, or to the left on the periodic table, has this pattern. If it was oxygen or higher, it would be the pattern 1, 2, 2, 1. Okay? So these two levels right here where my pen is would swap if you were oxygen or to the right on the periodic table. So oxygen, fluorine, or neon would be swapped. The way I've drawn it, this will work for really lithium through nitrogen. All right? So connect the dots, make it beautified to show where things come from. Okay, so I'm connecting these dots just to show where those center orbitals, called the molecular orbitals, come from. Now I want to name these. My class, I gave you a little hint. If you see 2 lines, what kind of orbital is it? Pi. Yeah, so anytime you see 2 lines right in a row, it has to be a pi for our class. And just like below, when you see 1 line all by itself, like these 2 or these 2, it's sigma. That's an easy way to remember which one it is. Is there 1 line there, or is there 2 lines? A sigma bond means the bond happens where? Where's the bond occurring? In the middle between the nuclei. The pi bond is occurring, yeah, usually like above and below or in front and back, not in the center. So which one, if it rotates, will break? Pi or sigma? Pi will break if it rotates. All right, the top ones are star, representing antibonding, and the subscript is 2p, and that's it. Cool. Simple enough? Does that make sense? Is it the same thing you do every time? I don't even know what the molecule is. I don't care. Now, I will care in a second, but to this point, I have not cared. All right. So I have pretty much generated almost the full thing here. If this is worth 20 or 30 points on final, you've just generated quite a few points. Okay, the last thing left is really to fill in the electrons, okay? And that's the only thing that changes on any given diagram. Okay, we're ready for you to reveal your molecule. N2 plus 1. Okay, you picked something that could possibly exist. That's good. I'm always nervous when I do this. Okay, so it's N2 plus 1. So how you draw that is one side is an N and the other side is an N plus, meaning those N's came from two different sides and one of them must be carrying that plus charge. Doesn't matter which one. So you can put the plus on the left or the right. All right. So now what you're going to do below these atoms is write the electronic configuration. So I'll do it right here. N is 1s2, 2s2, 2p, should be 3. Yeah. And N plus is 1s2, 2s2, 2p, 2. All right, and 2p2 because it's just plus 1. And now let's fill it in. I don't have a 1s orbital because it's core. I didn't need to do that. But the 2s. Okay, there's 2 electrons from each side. So I'm going to put 2 here and 2 here. And then fill in just that orbital to start with. 2 from each side, total 4. So if you don't know how to fill it in, watch my pen. Go in this order. 1, 2, and then up here 3, and then 4. Okay, now for the top, it's 2p3 over here on the left and 2p2 on the right. So 3 on the left, 2 on the right for a total of 5. So watch my pen again if you don't know how to fill this in. 1, now unpaired 2, 3 paired, 4 paired, and then finally 5. Okay? So there we go. The 2 common questions, so that you're done with your MO diagram, the 2 common questions are, what kind of magnetism is this? Paramagnetic. How did you know that? That's correct. Yeah, really, it's just because of that one unpaired one right there. So this will respond to a magnetic field, and because that one electron on the top middle is unpaired, this is paramagnetic. Okay, if they were all paired, you call it diamagnetic. The second thing I was asking for is the bond order. I don't know if all the classes do it the same way as I do, but what I do is only look at the uppermost diagram. In our case, that's a 2p. So the first number you need is the number of electrons in bonding molecular orbitals. That is 5. 1, 2, 3, 4, 5. Minus the number of electrons in antibonding. 0. None of them are in the stars. None of them are up there. So 5 halves or 2.5. So it's between a double bond and a triple bond. So we would not be able to draw this using Lewis. But this is the equivalent diagram for MO. And this is it. Really, it doesn't get harder or easier than this. And if you get it down, it should feel like, maybe not this point, but by the time you get the final, this should feel like a free 20 or 30 points. Because you're just doing this. That's it. Okay, any questions before I move on? I'm done with MO unless you have a question. Okay, you can discuss. That's fine. I know you Barov's class, they like to talk about stuff. Okay. So yeah, there is a question, yes. Where are you? Raise your hand if you have a question. Hi, yes. The question is, do you have to draw the template or will you be given that? I can't answer that question. Yeah. So. No, well. Yes. What did you ask for bond length? No, there's no way you could estimate bond length at this point, but it's relatively short because it's between a double and a triple bond. Yes, up there. Whoa, you need to like scream it out, unfortunately. Hold up, hold up. Okay, go ahead. Okay, Hayashi, okay, you foolish Hayashi people out there. He did sigma, for the two P's up there, he did sigma pi pi sigma. That's true if you're at oxygen or fluorine or neon. Only. If you're at nitrogen, all the way down to lithium, it's this. So there's two different pictures that you have to know. Yep. So Hayashi people, if you didn't know that, now you do, good. Okay, yes. Homonuclear on the final means both atoms are identical. Both nitrogen in this case. And it will be a diatomic, that's correct, yes. That's right. No. Yeah, let me repeat what this guy's saying here. Because from the N to the N plus, make sure you take that electron from the last orbital filled. That's right. There's the only exception you know would be like the transition metals, but that wouldn't apply to an MO diagram. All right, maybe one or two more questions I need to move on. Yeah. Yeah, that's right. I'll repeat your question. You're totally right. If I had N2, 2 plus, you could do this two different ways. You could, if you had N2, 2 plus, you could put an N plus on each side, or one side neutral N and the other side N 2 plus. That is totally correct. All right, are we ready to move on? I hope so. There's a lot more stuff to do. Here we go. Cool. Let's just do valence bond theory really quickly. Oh, and I'll change the pen colors. Valence bond theory. All it says is this, is because the p orbitals are at 90 degrees to each other, so they're at 90 degrees to each other, like that, from just the orbitals, you would expect every bond angle to be 90 degrees. Because p orbitals are at 90 degrees to each other. However, that doesn't turn out to be so, and so then we move on to either VSEPR or hybridization to help explain why that happens. Okay, so that's it. It's just conceptual for valence bond theory. All valence bond theory says is that because orbitals like p orbitals are at 90 degrees to each other, we expect bond angles to be 90 degrees. But we know from VSEPR and experiment that that's not true. So we use hybridization to explain how we get like a tetrahedral 109.5. That's all there is to valence bond. Really, all this kind of question could be as a multiple choice if it's on the final. Next I had hybridization. That's a good transition to hybridization. Here's what I know for hybridization. Count the groups on the central atoms, and then you can figure out the hybridization. And I would, if I were you, especially if you think you will become forgetful or freak out on the final, write this table on as one of the first things you do on the final. So, if you're hybridized with 2 groups, that's SP. 3 groups is SP3. Oh, no, SP2. 4 groups is SP3. So you see, as I add groups, I'm adding p orbitals to the type of hybridization. When I cannot put SP4, why not? There's only 3 p orbitals. So the next one is SP3D, and then SP3D2. So if you know the number of groups, you can figure out what the hybridization is really easy. One group is really not hybridized, usually, is what most people say. So it'll either be an unhybridized s or p orbital. Okay, so that's one thing that's important to know for hybridization. Kind of paired with hybridization is the following things: the bond and the type of bond. Okay? So we know single, double, and triple bonds in our class. A single bond is a sigma bond. A double bond is a sigma and a pi bond. And a triple bond is a sigma and 2 pi bonds. So notice that every bond has a sigma bond, but only double and triples add pi's to it. That what gets you to the second and the third bond. So that's double and triple bonds can't rotate. You can't rotate. Okay. All right, so those are two common things. The other thing about this, and then I'll show you some examples, would be if you take, I'm going to kind of write carbon as our example here. Carbon is 2s2, this will be carbon, 2p2. Okay? When this hybridizes, it can hybridize one of 3 ways. Okay, so I'm going to draw all 3 ways. If the carbon wants to make a tetrahedral shape, then, as you saw in the previous table, it will sp3 hybridize. All 4 of these orbitals will mix to make 4 new orbitals with 1 electron in each. Okay? So it'll look like that. That will give it its tetrahedral 109.5 degree bond angles. If it decides, hey, I don't want to do that, I want to instead form a trigonoplanar shape, then it will hybridize 1 of the s and 2 of the p's and leave 1 of the 2 p's unhybridized. Each one will get 1 electron, and that will be the hybridization scheme. If it decides, no, I want to hybridize so that I get a linear shape, so this one would be trigonoplanar. This one will be linear. If it wants to get the linear shape, 1 of the s and 1 of the p's will hybridize, and 2 of the 2 p's will stay unhybridized. Each one getting 1 electron, and that will be its hybridization scheme. Okay? Those hybridization schemes you'll need to know. The only thing that could possibly change, if you change the atom, what do you think would change if I change the atom? Number of electrons. So for example, if I had nitrogen, which has 1 more electron, right? Then I would add, for this diagram, 1 electron right here, where my pen is. Or for this diagram, 1 electron right there. Or for this diagram, 1 electron right there. Okay? Okay, hybridized orbitals. These hybridized orbitals form what kind of bond? Sigmas. The unhybridized 2p orbitals form pi bonds. That's right. Okay? So I'll show you an example in a little bit. Okay, so let's say I gave you a molecule. I'll put it down here. There's a couple questions we could ask you about. And we'll do another example in just a minute. But let's say I gave you this one. There we go. That's naphthalene, or mothballs are made out of that. Okay? So let's say you have this molecule. Some common questions I would ask you. What's the hybridization of each atom? How many sigma bonds do you see? How many pi bonds do you see? All right, do you want like a 30-second head start on me? Go for it. This is what I want to know. Hybridization, sigma, pi. I want all that information. Go for it. You got it. 30-second minute head start. You can talk to your neighbor if you want to. Get your cheating out right now. Talk to your neighbor. While you're doing that, I will get my next example ready for Lewis. Hybridization for every single atom. You better tell me for every single atom. Yeah, heck yeah. Don't be messing around. I want to give you an easy problem. All right, I already found my problem for the next one. Don't be messing around. Hybridization of all atoms are the same, and that is sp2. All of them are sp2. Do you need me to do any of them for you? Yeah? Okay. Okay, well let's do the easier one first. We'll wait for that one for a second. How many pi bonds are there? 5. You just count each double bond counts as 1 pi, so you should get 5. Okay. Anybody get the total number of sigma bonds?
11.
I'd say it's definitely more than 10. Okay, let's see. Let me count it out for you. Every single bond counts as a sigma, right? Okay, so I'm going to count. This is how I do it. I go around the rings first. 1, 2, 3, 4, 5, 6, correct? 7, 8, 9, 10, 11, correct? I hope you didn't say 11 though. Because every carbon has how many bonds? 4. Uh-oh, you didn't draw in the hydrogens. Okay, so that we were 11, right? Okay, 10, 11, no, we were 11. 12, 13, 14, 15, 16, 17, 18, 19. Anybody else get 19? Yeah? Yeah, good. Okay, remember, you gotta remember, every time you do one of these problems, every carbon has 4 bonds. Okay. So if you look at any of these carbons, take this one for example, there's 3 groups. This single bond, and a double. 3 groups, sp2. If you look at any other carbon, say this one right here, there's a double bond, a single, and a single. 3 groups, sp2. All of these are sp2 as I've drawn it. So they're all what shape? Trigonal, planar, and they all have what bond angle? 120, that's right. Okay? Any questions on this before I go to my next problem, which is a Lewis example? Okay, all right. Each carbon, I said, must have 4 bonds. So if you don't see 4 bonds, draw on a hydrogen where that 4th bond is missing. Okay, yes? Oh, by the way, anybody who wants to start on this, go ahead. That's our next problem. Yeah? Does hybridization automatically occur? That's correct. Okay. I have a tough Lewis example. I assume you appreciate tough examples. This example, we're going to do everything that could possibly be attached to Lewis. That means whenever we ask you a Lewis question, we could also ask you shape. We could ask you, which there's 2, the electronic and the molecular. There's also the bond angle. There's bond order. There's, let's see, formal charges we can ask you. What else can we ask you? Number of sigma bonds, number of pi bonds, hybridization. All that stuff goes with Lewis. So one single Lewis example could go into all those areas. All right. Oh, polarity, that one too. All right, I'm going to move this over. We have this I5 minus. You're actually going to use this in 2B and 2C to do what's called a starch titration. All right, so let's try this. We got to draw it out. I5 minus. I'll start with the valence electrons. Okay, there's 5 iodines and column 7, plus 1 electron to the minus. That's a total of 36. All right, now this, it tells us, it gives us a huge hint. It's going to be in the shape of a V. That means don't draw this in the shape of a ring, because a ring looks more like an O than a V. Does that make sense? So So I would more likely draw something like this as my first try at a skeleton. Just eyes all lined up in a row, and hopefully it bends such that it looks like the letter V. Okay? All right, and so far each bond remembers 2 electrons, so 2, 4, 6, 8. I've used 8 electrons of a total of 36. 8 of 36. Now, if you're following my style, people in my class know to now go to the terminal or most outermost atoms. Those are the 2 iodines on the outside. So 2, 4, 6, 8, 10, 12, 14. That has an octet. Now go over here. 16, 18, 20. That has an octet. 20 of 36 now. So now go to the center ones. Where was it? 20, 22, 24, 26, 28, 30, 32. So now I'm at 32 of 36, and everything has an octet. I have 4 electrons left. Where do you want them to go? Okay. I heard a lot of centers, so we can try that. If you're wrong, you will know pretty fast. If you're right, that's awesome. All right, if we put it on the center, let's work this out. First of all, let's look at these 2 because they have the same number of groups here. So this one and this, that atom and that one. How many groups? 4 groups. So 4 groups, what's the electronic geometry? Tetrahedral. If 4 groups have 2 lone pairs, that is called bent. Okay, so those 2 are bent. This is not, you know, as somebody who knows what the letter V looks like, not sounding good. Because I'm probably looking at something like that. To me, that doesn't look like a letter V. Maybe to you. Okay? So, this is wrong, definitely. Okay, let's go back to where we were. Does that make sense why that's wrong? These 2 are bent. That's not going to make a letter V. Okay, not that kind of letter V. Alright, so we'll go back. And this happens sometimes. You just don't get what you were hoping for. So let's fill in those electrons to where we were just a moment ago. Okay. So now where do you want to put the 4 electrons? Not on the centermost one, but let's split the difference between these 2. Is that okay? So a pair here and a pair here. Let's do that. Is that okay that I'm breaking the octet? Yeah, because anything below the carbon row on the periodic table can break the octet. Anything below the carbon row. All right. This shape is, yeah, electronic geometry would be tetrahedral, but the molecular shape would be bent. That's sounding good for the letter V. Okay, both of these are the same. How many groups? Should count 5. So the electronic shape is trigonal bipyramidal. Trigonal bipyramidal. And so the molecular geometry with 3 lone pairs is called linear. That's sounding really good. Okay, let me redraw this in the correct V formation. One more time. Here's what it would look like. Let's put in our electrons. So if we ask you to draw something on the final, I highly recommend, sometimes we don't, but if we do, draw it to the correct 3-dimensional structure is my recommendation. Because this has a -1 charge, you put brackets around it and put a -1 there. And now let's fill in everything we know about it. I'll put EG for electronic geometry is tetrahedral for the center one. The molecular geometry for the center one is bent. The bond angle, this is the ideal bond angle. That's all you need to know. You don't have to memorize the actual bond angle. For these 2 iodines, the electronic geometry you told me was trigonal bipyramidal. And the molecular geometry of 3 lone pairs is linear. So that's this iodine and then the iodine over there. You don't do shape for terminal 1, so you won't have to do it for those last iodines. And then the bond angle for linear is 180 degrees. That looks like a V. How many pi bonds? 0. There's no double bonds. How many sigmas? 4. There's 4 single bonds. So 4 sigmas. I will give you a moment. I'll give you a head start on me. Determine the hybridization of all 3 of these center atoms. Go for it. I'll give you about a 20-second head start on me. Hybridization, all 3 of these. The very center one is? SP3. It has 4 groups. These 2 are both the same. They are SP3D. Sometimes people will write the D in front. It's the same thing. So you can also write DSP3. Same thing. Polarity. Polar or non-polar? Polar. It's totally asymmetric. And that's how we do it in my class. I don't know how the other classes do it. So this is definitely polar. Does anybody need me to explain that? Or you have a separate question? Or the polar of my class or your different class? Yeah, I recognize that. That was not my name. Okay, this is how I explain it. You can tell me if this is how you explained it in class. You look at it, and you ask yourself, does this look fully symmetric? I would say no, because on the top there's 4 iodines. From the top of center, 4 iodines, but on the bottom there's not 4 iodines. So an X would be symmetrical. But this one, as a bent shape, it's asymmetrical with respect to the center iodine. So I would say no, it's not symmetrical. Anything that is not symmetrical is polar. Anything that is symmetrical is non-polar. That's how I did it. How did Hayashi do it in your class?
Electronegativity.
Electronegativity difference. That could be a little confusing here because they're all the same atom. Right. Okay, you can do it that way too if you can figure it out. Okay. Yeah, polar though for sure, Did I miss? I think I got everything. Oh, all the bond orders are what? Yeah, every bond order is 1 because they're all single bonds. Any other questions on this?
Formal charge?
Oh, formal charge. Thank you. Thank you. Let me give you a head start. Find the formal charge of all center atoms. Oh, actually, all atoms. Find the formal charge of every single atom here. Go for it. Okay, here we go. Terminal atoms. What did you get a formal charge of? Both outside zeros. Okay, the one at the middle of the V. What do you get? It's 1. Is it positive or negative? Plus. 1, 2, 3, 4, 5, 6. It's plus. So these 2 are? Yeah, these 2 are negative. Do I need to do any of those? Raise your hand. This is your last chance. Okay, which one? All of them. Okay. Again, I do this different than sometimes other classes. So if you have your own style, don't listen to me. Okay, you look at iodine on the periodic table. It's in column 7. So you should find 7 items around it. When we look and count, I find 1, 2, 3, 4, 5, 6, 7. So it's a 0. Same for this one. 1, 2, 3, 4, 5, 6, 7. 0. Look at the middle one. You count 1, 2, 3, 4, 5, 6 items around it. It's short by 1 of 7, so it's a plus. These are 1, 2, 3, 4, 5, 6, 7, 8. It's over by 1 by electronic ions, so they're both negative. That's how I do it. Do your classes do it differently? Or you don't know? Okay, that's cool. Yeah, question, slow. Oh, hold up, a much louder, one more time. Oh, can I change the structure to decrease the number of formal charges? This is pretty good. Remember, a formal charge of +1 is -1, that's fine. And because it has an overall charge of -1, I am expecting a formal charge to not be 0, at least 1. You might be thinking to make a double bond somewhere. You'd have to double check to see if that changed the shape though from B, would be the only loss. I think this is the one I would accept on a final, but there could be some variations I'm not thinking of. Yes? Does the shape trump the formal charge? Well, the formal charge is good, so that's not actually an issue. Maybe it could be better, but because it was told to you that it's V-shaped, that must trump anything else. Yeah. If I didn't say that, then you could do whatever you want. Yes? The MO diagram? Okay, the question is why this is bond order, but on an MO diagram there's also bond order. They're the same thing, but they have a different method of calculation. They tell you what kind of bond it is. But on an MO diagram there's actually a math formula. On this one you just look at it. So it's easier to lose. Okay. Yes? How do I get the bond order? I just looked at it, I saw single bond, and single means 1. That's it. Double would be 2, etc. Yeah. Say it again. Okay, let's say, since you all are into bond order, let's just do a different molecule. Really quickly, then I need to move on. If it was this kind of example where there are different bonds, this would be a bond order of 1, and this one would be bond order of 3. Okay? Yeah, every bond has a different bond order. That is correct. You don't need to do an average here. That doesn't apply. Averages only apply with resonance structures. So, for example, wow, you all are really excited about bond orders. Let's say we have this. These are resonance structures of each other. What is the bond order of that bond right there? Well, not 2 exactly, because it's 1 here. You see what I mean? So what's the bond order? Yeah, if it's a bond that comes from a resonance structure, then what you do is you take, well, it's 2 here, it's 1 here, let's average that over the total number of molecules, 2 in this case, and this is a 1.5 bond. Somewhere between a single and a double bond. So if you want, you could see 3 ways to get to bond order. In MO theory, it's just a formula. For most molecules, like the top one, you just look at it. If the molecule has resonance structure, you have to take the average. Okay? Those are the 3 possible situations. Yes? If it had resonance in all places, if it was trigonal bipyramidal and it had resonance in all 5 locations, and they were all equivalent, then you'd have to divide by 5. Because there's 5 bonds. That's right. I can't even think of an example where that would happen, but if it did, yes. 5 by 5. Because that had 5. At least, it might be more. Depends how many resonance. It's divided by the number of total resonance structures. Okay. Can we move on? Yeah, okay, let's do it. Let me say a little bit about trends. Here's my recommendation on trends. Let's say this is a periodic table, okay? And fluorine's over here, and like cesium, barium, francium, etc. are down here. What I would do when I walk into the final, the first thing, because this is something I would think I would forget, is I would draw all my trends on the periodic table so I don't forget them, okay? So, for example, what goes this way increasing? Radius, shielding, right? What goes this way? Yeah. Ionization. I'll just write it here, I guess. Ionization energy, is that a positive or negative number? Positive. What else? Electron affinity goes this way. That is a what number? Negative. What else? Electronegativity goes this way. That's a positive number if you want to know. And then, what else? Yeah, Z effective, only along a row, this way as well. You're also missing, yeah, metallic character also goes this way. So, francium has the most metallic character, fluorine has the least metallic character, or is the most non-metal. Okay, am I missing? What else? Let's see, here's the staircase. Which side are acidic oxides and which side are basic oxides? These are acidic oxides, these are basic oxides. Are metals good reducing agents or good oxidizing agents? Okay, maybe we'll think about this for a second. Do metals want to lose an electron or gain an electron? Losing electrons is oxidation, so what does that say about its agency? Yeah, these are reducing agents. So thus these are oxidizing agents. Is that okay? I think that's all the trends you were supposed to know, unless somebody can think of another one I missed. Radius is right there. Okay, cool. See, this is chapter 8, right there on one page, basically. What else, what's really the only calculation in chapter 8? What's the only calculation in this chapter? Not really Z effective. Ionization energy. That's how I read the formula. Okay. That'll be given on the final though, I'm pretty sure. All right. I'm ready to go on. Yes. Would you have to calculate Z effective? Well, really, this is Z effective right there. This is technically Z effective, though we have avoided the issue at all costs. Yeah. It's a little messy, that's why. Yeah. Yes? If an atom is given atomic, that would be true if it's hydrogen, the atomic number is 1. If the atom would have to be given to do a calculation, and so if you had neon, you should put a 10 here. Yeah. Okay. Let's move on. Okay, those of you who want to go because you got your fill, that's totally fine. We're going to move on to this section right here. Let's do it. Okay, we need to keep moving. Okay, electron configurations. We already did a few, let me just say a little bit. Somebody wants to know about the exceptions. There's really 2 exceptions that you need to know, and those happen in the transition metals. So, you need to know that everything's normal except for the following. If you're in the 4th or 9th row of the transition metals, the 4th row is the chromium column. See the chromium column, chromium, molybdenum, or the copper column. So copper, silver, gold. Those half fill the S before filling the D. Those half fill the S before filling the D. That's your first exception. The second exception is that when you're removing electrons from the transition metals, so you're making a cation, then you're going to remove the S before the D's. Those are the only 2 exceptions. They don't apply elsewhere. They just apply here. Okay. Nope. Okay. So let's see. Does somebody want to give me an atom? Boron? Sweet. That's super easy, are you sure? Platinum. Let's do platinum. That's a little tougher. Yeah. You want a charge on it? +1? Minus wouldn't make sense. What's the previous noble gas? For platinum, that would be xenon. Why would I not pick radon? A really simple way is to look, is 86 bigger than 78? If it is, don't pick that number. And so I want the number closest to it without going over, so 54, or xenon, is definitely where I want to go. Okay, what's my next energy level? 1, 2, 3, 4, 5, 6s2. So let's do this first for platinum neutral. I think it'll be easier, and then we'll do platinum plus. So 6s2 for platinum neutral. And then what's the next level? Yeah, according to this periodic table, the next one would be the F's. Is it the 4F or the 5F? 4F. What's my superscript? 14, because it's totally full. And then what's the next level? 5D, and neutral platinum counts up to what? Okay, I believe you. Yes, 8. All right, so if I was going to do this one, what I would do is I'm going to remove from the S first because it's a transition metal. So it'd be 6S1 for F14, 5D8. Instead of removing from the D, I'll remove from the S first. The next electron I remove is also from the 6s. After that, I go to the D's. Yes. I don't know what it is. Oh, that what you're asking doesn't matter. You don't have to fill the D's one at a time necessarily because we're past the X. All right. That's all I got with electron configuration. My recommendation was to redox. That's the most commonly missed, not hard problem on a final. So let's do a redox. Do you want, you get to choose your own adventure here. Redox, let's see, what binder is that? Yes. You get to choose your own adventure. Do you want a redox that is difficult because it's mathematically difficult? Or do you want it, which is hard, granted that's harder than you would think. It has other difficulties too. Or, and I would consider both these problems of equal level difficulty on a final. Or one that's a little bit conceptual. Equal level. No, you gotta pick one, I'm sorry. Conceptual. You want to pick a conceptual, okay. Hopefully, have you done this in your classes yet? Okay. This is mathematically not too hard, but conceptually a little bit difficult. All right. So let's try this. See if you can write the half reactions, and then we'll giggle later. Okay. See, I'll just give you a moment. See if you can possibly write the half reactions. If you can get these half reactions, you are doing extremely well. Because they're a little tough. Okay. 10 more seconds. All right, if you're still working on it, go ahead. First, I would work on the charges, if you haven't done that. Hydrogen H2 is not charged, but this is oxidation state, 0. O2 oxidation state, 0. Oxygen here, no, not 0. -2, hydrogen is +1. Okay? So what is oxidized? The hydrogen is oxidized, it increases in oxidation state, so the oxygen is reduced. Okay? So, if you know your 4 steps of balancing the half reaction, step 1 is by inspection balancing what's not oxygen or hydrogen. Step 2 is balancing the oxygens with water. Step 3 is the hydrogens with H+, and step 4 is the charge with electrons. Sound familiar? Okay. So, see how water is in one of those steps? Okay. I would highly recommend you just ignore this. Pretend it's not there. because it's in one of your adding steps. So I recommend if you see water, H plus or OH minus, you ignore it. If we give it to you here, we're just messing with you. Okay, we like to do that, it's fun. Okay? So if you see water, H plus or OH minus, I would ignore it because you will add it in later. Why would I recommend you ignore it? Because which half reaction will you put it in? If you don't want to guess the wrong one. Correct? Okay. So, here's your half reactions. Let's see if anybody got them. First one is this one, and the second one's this one. Pre-balanced. Pre-balanced. Anybody get that? Cool, good, I did this. Okay, all right. Do you see why this is true now? I'm ignoring water because you don't know which half reaction it's going to go into. It will magically appear later. Don't worry about that. Okay, let's do the oxygen first. Okay? Step one, balance whatever's not oxygen or hydrogen. So that doesn't apply here. Just oxygen and hydrogen. Step two, balance the oxygen with water. Oh, here's where the water goes. You didn't know to put it here. You're messed up. Okay, that was supposed to go here. But you wouldn't have known that necessarily. Now, balance H plus, hydrogens with H plus. So 4 here, 4 H plus here. Last step is balance the charge with what? Electrons, and I'll need 4 electrons right here. Is that all cool? Any questions on that one? Before I go to the next one. Next one, step 1. Balance whatever is not oxygen or hydrogen. Doesn't apply here. Step 2, balance the oxygens. Doesn't apply. No oxygen. Step 3, balance the hydrogens. 2 hydrogens. So I need 2 H pluses. Last step, charge. It's 0 here plus 2 here, so I need 2 electrons. There's my 2 finished half reactions. Which one is the reduction half reaction, top or bottom? Which one is the reduction half reaction? Reduction, oxidation. All right, now, get a different color pen. Multiply this craziness. I multiply the top by what and the bottom by what? 2 and 1. So, 2H2 and plus 4H plus. So I'm writing out all the reactants, and then I'll do all the products now. 4H plus 2H2O. Okay, notice that the H pluses drop out. So I am left with 2H2 plus O2 goes to H2O. 2 H2Os. And we're done. If you were also somewhat intelligent, you could have just done that from here. 2, 2. That's okay. If we force you to do it with a half reaction, you have to do it that way. Okay. Any questions? So I would consider this a pretty conceptually difficult problem because of the half reaction. Does it make sense now? Yeah, okay. This kind person right here, I just stole their notebook. Did it like this. If you don't know where to put the H and you put the waters wherever, you can still work it out. It will still work out to the right answer. It'll just be messier, and you have a higher chance for miscalculation. So that's why I recommend students usually don't do it. But if you want to, you can. That's fine. Yeah? What are you talking about? The 2 electrons? How did I get this? Well, anything, the question is oxidation states. Anything that's elemental is always 0. And then oxygen is usually -2 on most compounds, and hydrogen is usually +1, just from the periodic table. Okay? You like that example? Not bad, huh? Okay, yes. Oh yeah, good question. If I solve this using acidic conditions, what would be the basic conditions answer? It's the same answer because there's no H pluses. That's why in this question, this was actually an exam question from before, and we did not label if it was acidic or basic conditions because it didn't matter. We just let you worry about it. Okay? All right. Yes? The overall charge of water is 0, that's right. Okay, maybe I didn't get it. You can ask me after. Okay. Oh my gosh. I think I can only do one more of these. I know.
Wait, what's in our team?
Wait.
Wavelength.
Okay. I've been hearing these two the loudest.
Wavelength.
So, one person want to recommend something else?
Stoichiometry.
Between these two, right? Okay. Huh? This is not wavelength. This is wave function.
Wave function!
Okay. You get to both. Between Dalton and wave functions. Who wants Dalton? Dalton. Okay. Wave function. Okay. And then we'll go just one-on-one questions. Okay. Or not one-on-one, but specific questions. How's the review going so far? People from other classes are doing okay? Alright, I'm glad. Okay, do you want me to go through the 2D and the 3D wave function? Yes or no? Okay. I just wondered, I don't want to do something you don't want. Okay. Okay, what happened in chapter 7 is that they introduced the topic of a wave function by first introducing it in 2 dimensions, and they called that the particle in a box, or they did it in 2D space. That was where the wave function, and I think we give this to you on the exam. They slightly switched the last page in the last couple days, so my class, I have to resend out the last page of the final. Which is the formula page. Did the other classes send that out yet? Oh, they're losers. Huh? This is one of the instructors actually highly requested we have this formula on there. So, I don't know which one, it just came to me with it there, and they said it has to be there. So, that function describes a particle in a box. You don't have to have this memorized because we give it to you. But if we look at that for a moment down here, if you get a function like this, kind of some common questions that you could be asked is how many nodes are there? Nodes are where it intersects what? The x-axis, yeah, so this would be psi, and this would be the x-axis here. So there are 1, 2, 3 nodes. So the number of nodes are just where it intersects the axis. There's 3 nodes here, in this case. Otherwise, there's not a lot that we can ask you outside of that. We can ask you what n is. Does anybody know what n would be? 4, because n is nodes. I'll write like this, is n minus 1. So if there's 3 nodes, n must be 4. N is that same principal quantum number that you know from quantum mechanics. So there's n, l, m sub l, m sub s. They're basically cousins. They're almost the same thing, but it's equivalent in 2D space. So that's n. That's kind of the stuff about all you would get out of this one. Okay, but it was sort of setting you up for 3D space. That's a little more significant for us. What do you need the equation for? Well, I guess if you wanted to plot this. Okay, let me back up for a second. Okay, let's just think like good thinkers for a second. Let's assume your professor is benevolent. Okay? So you have a kind professor. Theoretically, because we all made the final together, if they saw examples on the final that your class could not do, they would say, stop everybody. We can't have this question on the exam. Let's remove it for the sake of my students. Okay? I don't know if your instructors did that. I did that. Okay. So, I don't know. I'm not in your class. I have no idea what happens. Okay. So, if there is information that an instructor did not cover, and they are benevolent, what does that mean? That makes sense to me. Okay, so you would need to think, ideally, if you were going to all 5 classes, you would know what other instructors didn't cover, and then you wouldn't study that thing for the final, if you assumed that instructor was benevolent. Does that make sense? Does that make sense? That makes sense to me. Okay. Do you need to talk about that? Yeah. Got it. What do you want to say? Oh, God. I hate to answer that question. I'm not going to answer that question. So, you can ask me that. So 3D is a little more relevant. The 3-dimensional wave function is a little complex because it's a function of 3D space, which is hard for us. It has a radial and angular part of the wave function. But the nice part about it is, as I explained in my class, if you know your quantum numbers, then it makes the 3-dimensional wave function much simpler. So for example, if I gave you, let's say a 4pz orbital, okay? You could use that on the top, that equation, if you have the equations for it. I can't remember if we give it to you on the final. Did I sent that out to my class. Were those equations on there?
No.
Were those 3-dimensional equations on there?
No.
Okay, some people think no, so we couldn't have you use them if they're not on there. But you could use that to plot this function and draw it, or if you know these quantum numbers, you could say that n is what? The first number, 4. You could say that L is the letter P, which is what number? 1. And now, you could also say the nodes. How many nodes are there? Yeah, 4 minus 1, or n minus 1. There's 3 nodes. So, you would say, oh, I know what that looks like. That's a PZ, 4PZ, so this is on the z-axis. And there's 3 nodes. Where are those nodes? One's right here in the middle. It's called an angular node. That's one of the 3 nodes. Where are the other 2 nodes?
Radial.
Yeah, they're called radial nodes, and they're circumscribed circles inside of here. So here's your 2 radial nodes, for a total of 3 nodes. I would definitely know how to calculate nodes and know what the quantum numbers are. Okay, so 3 in this case. So that saves you, for those of you wondering about the wave function, from knowing how to manipulate those equations. Is there a question from this? I see there's a disturbance in the matrix. All right, well, I guess I'll just end by saying I hope you enjoyed it. When you become rich and famous, invite my family to your new resort that you want purchased in the Bahamas or Rhode Island, and I'll see you there. Otherwise, have a good final. For those of you who want to stay and ask specific questions, wait about 30 seconds. Okay, well done. Those of you leaving, leave quietly, please. Those of you staying, it's time to ask specific questions. So I believe I brought my practice exams. I also have the worksheet I made for you, or my class. So if you have a question, please tell me the number, or the page number it comes from, etc. Here we go. Yes? Page 177 of my practice exam reader. Number what? Okay, that's this question. This is follow 9. H2SO4 is the question one. H2SO4. Do you want me to draw the Lewis structure, or do you want me to draw it with you, or should I just draw it because I know what it is? Okay, I'll just draw it because I know what it is. You should have got for the Lewis structure the following. You should have got that. It could be rotated in space, but that's what you should have got. That's the best Lewis structure. Formal charge is at 0 everywhere. In fact, I'll give you a hint. Remember, the best formal charge is 0. And look, all zeros. If you don't know what to guess in this column, or you don't have time, just guess zeros all the way down. If we ask you that. Because it's the most likely answer. You could be wrong, but if you have limited time, who cares, right? Okay. So now polarity, you're curious about this? Huh? Aha. It looks nonpolar. What's the problem with saying this is nonpolar as I drew it? I did not draw the shape correctly yet. How many groups are on that center of sulfur? 4, so it is tetrahedral. And there's 2 other center atoms, they're both the same. 4 groups, 2 lone pairs. What's the molecular geometry? Bent. So now you can kind of understand, we did not ask you to draw it, but if you drew it, you would fully see it has to be polar because it looks totally asymmetric. This is bent. This is also bent. You can see how asymmetric it looks. Is that okay? We didn't ask you to draw that, though that's something you should be able to draw. You can see it's totally polar. Yeah. An easier way to do this, a tetrahedral compound is always polar if all 4 groups are not the same. So these 4 groups had to be identical for this to be called nonpolar. Okay? All right, next, yes? Page 209 in my practice exam reader. Question on this one, yes? How do you know S is the central atom? Because you have S is the only lone one listed. And then there's lists of atoms around it. Meaning there's more than one atom next to the lone sole S. What's that? Oh. How do you know O is not going to be a middle? So there's a couple ways you can know that. One is, if you tried the Lewis structure for that, it probably would look a little weird and not all 0 formal charges. The second reason is, a quicker reason, if you have a acid, okay, or a polyatomic anion, remember those from chapter 3? Sulfate is one of those. The oxygens are always going to be on the outermost edges, okay? Well, I just noticed that that's a little disturbing. Good luck. That's so funny. Okay, yes. How did I know how to place the oxygens around the tetrahedral shape? It doesn't matter. You can put them anywhere you want to, it's the same molecule. Okay. I drew it, the reason I drew it that way, that if you try the other ways, this is the easiest to draw for non-artists. Okay. Now, 209, number 8. This one. Okay. Do you want me to run through it, or did you have a particular question? Okay. So for this, I have to move this out of the way. There's some action going on right here. So I have lead 204, I think, yeah. It has an abundance of 1.48%. Of all lead, this is less than 2%, okay? That's what that means. Okay. And I have a block of lead. So I have some block of just straight up lead. I know this percent of this lead is 204. The rest of it is anything else. Okay, the density, I know its density is 1.35 grams per cubic centimeter. There's the density of lead. I know that, we know the number of atoms in this thing. There's 8.34 times 10 to the 21 atoms in that block. So somebody went in and counted the atoms, but what they don't know is, what do they not know? Oh, the volume. They don't know the volume. Okay, so density is mass over volume. That's cool, right? So once you have density, you do have that. Once you have mass, you're set. Is that okay? You just plug it into the formula. So let's work on mass. We have 8.34 times 10 to the 21 atoms. Okay, and I know that there's 6.022 times 10 to the 23rd atoms per mole of lead. Is that okay? And then look at the periodic table for lead. It's 207.2. Yep. 207.2 grams per mole. That is grams, though, of all lead. Is that okay? That's grams of all lead. And this one has, So, this is grams of all lead, but I have lead, only 1.48% or is lead 204. And let's see what else it says. This contains, hold up. This is, sorry, I missed one important detail. There's only that many atoms of lead 204. Okay, so this is moles of lead 204. All right, now here's the problem. I can't just straight up multiply by this to change to grams yet, because this is not for lead 204. Is that okay? Okay, so how do I use this percent to find out the total number of lead in this? Okay, let me say this another way. This is, of these atoms, so maybe focus there, maybe that'll be the easiest. 1.48% of all the lead is that number. So what does that mean I do? Anybody? 1.48% of that, of all lead is that number. There we go. There we go. Yeah. Okay, let me, since some of you didn't get it. 1.48% of normal lead, so that's times, is this number. The lead 204 number. So I need to take that and divide by the 1.48%, which change it to a fraction. Now I have all the lead atoms in there, and now I can multiply with this to get grams. And now you can solve your problem. Is that okay? So the key was divided by that number. That changes it from the lead you have to all lead. Okay, cool. Yes?
For electron configurations,
Yes.
exceptions for manganese and copper, does that apply to the entire column or just manganese and copper?
It's not manganese, it's chromium and copper columns, the exceptions. The fourth column, chromium is the fourth one over. And then the copper column. Those exceptions apply all the way down, though there are exceptions to that exception. And that exception to that exception is tungsten, but we wouldn't expect you to know that. Okay, yes. That's right. Because we have a question on this again. This, divided by this number, makes it normal lead. Divided by this number. Huh? Yes, and now I get the moles of normal lead. Really, this will be the moles of normal lead, and this will be the mass of normal lead. No, normal lead includes 204. I'll do the same thing back. Lead, this is a good question, good conceptual question. If I say I have something like any atom, lead, boron, whatever, it has multiple isotopes in it. So for example, carbon in your body, most of it's carbon-12, but there's also carbon-13 and 14. So just like lead, 1.48% of all lead is 204. So there's other lead in there too. Maybe 207, maybe some 208. You know, other isotopes of it. So this is some of it. So this gets you to all lead. You don't have to add anything else to this number. Okay. Yes?
If you were to add, you mentioned 101.48%. That's kind of what it's right there, right? You wouldn't add because you're going over 100.
That's right. You would be making more than 100%. If that doesn't make sense, come see me afterwards so we can talk more. Okay, next question. Yes?
Number 28 on
Fall 2000, okay. Hold up. Fall 09, 28. This one? Okay, a particular part or run through it or what are you looking at? A first part is not working for you? Okay. Number 28, Fall 09. Okay, there's two gas reaction tanks. The first tank contains oxygen gas. It's 1.23 liters, and it's 724 millimeters of mercury. The second tank is 2.05 liters. It contains nitrogen gas, and it's 698 torr. Oh, they're connected, it says. And there's a valve separating the two, so the valve is closed at first, but then it's open, and the O2 in here, unfortunately, reacts with the N2 to form N2O. And the temperature, it says, is 25 degrees C. What is the limiting reagent? Awesome. Nicely played, whoever wrote that question. So what's the limiting reagent? You know, we didn't have to use that word also. We could have just said how many moles of N2O is made. You would know it's a limiting reagent because they give you information about both reactants that leads to moles of each reactant. So when there's information about moles of more than one reactant, it is a limiting reagent problem. So because of that, you want to find moles of both of these. Let's also balance 2 and 2. I think we'll do it. So what I'm going to do is find the moles of oxygen using the ideal gas law, PV over RT. And we have all these numbers. Oxygen, 724 millimeters of mercury. So I need to multiply by 1 over 760 to get to atmospheres. Volume is 1.23 liters. R is 0.08206. And T is 298 Kelvin. So that, Let's see if it's even written on here. Then I just write it down. This would be awesome. It's 4.79 times 10 to the minus 2 moles. So there's O2. Okay, so far, whoever asked this? Yeah? Okay, same for N2. Can you kind of do the same pattern for N2? Is that okay? Okay, same thing for N2, just use the numbers on the right. Here, these numbers. The N2 related numbers. You'll get moles of that, which end up being 7.70 times 10 to the minus 2. Huh? Okay, cool. Oh, torr, millimeters, mercury, are the same. Yeah. Is that what you're talking about? Okay. Now, to do the limiting reagent, the way I do it is I start here, like say oxygen, find the moles of this one, and then use the nitrogen number to find the moles of N2O, see which one gives the smaller answer. Did you want me to run through that? Okay, so I'll do it for one of them, and then you do it for the other one. 4.79 times 10 to the minus 2 moles of O2. And then use a molar ratio. There's 2 moles of N2O for every 1 mole of O2. And I don't know if that number is written down. I think it is, yeah. It's 9.58 times 10 to the minus 2. That's moles of N2O. You would do the same, but starting with the nitrogen number as well. And you see which answer is smaller. Is that okay? Okay, cool. Next. Yes? Page 75? 175. What number? 11. Hold up. Oh, there. Yes. This number right here? Okay. What is this? Let's see. Oh, nice. Okay. This involves oxidation, reduction, or whatever. Okay. Let's see if it involves oxidation or reduction. This is -1. What's the charge of chlorine right here? -1 also. Hydrogen would be +1. It'd also be +1 here. What's the charge on oxygen is -2. What's the charge on carbon? +4. What's the charge on carbon here? +4 also. Hey, nothing changes in oxidation state. Is this a redox? No. So it can't be A, B, or D. So C or E. It doesn't look like combustion, so it's got to be C. And HCl, that's one of our strong acids. CO3 2- is a base because it receives the proton to become H2CO3 aqueous. Is that okay? Okay. You think about that. You think. Okay. Next. Yes.
Not ionized. So it's aqueous that is
The review worksheet. Oh gosh, I had that here a moment ago. I might have. Oh, it's over here. What number? Number 9 on the review worksheet. This is if you're not in my class, then you've never seen this. That's too bad. You have this reaction. Oh wait, number 9. For this reaction, number 7, you gotta do this problem. It's a 5-part problem. Was there a particular part that you were into? Only part A? A and B. Okay, A and B. So part A says that if there's 10 grams of P4O10, then what's the mass of phosphoric acid? Well, you need to balance the reaction. And then basically your calculation is you need the molar mass of this to get to moles. And then you need the molar ratio, the moles of phosphoric acid over the moles of P4O10. And let me see, since we didn't do that part, let me just skip over and find that number. You can't see it, you know? Just messing around. Here we go. A 4 and a 1. So is that okay for mass? I'll re-explain it. You go to moles using the molar mass, and then you use the molar ratio to go to moles of that one, and it finally wanted the mass, so you go one more step. Here's the molar mass of H3PO4. Here's the molar mass of B4HO10. Is that okay? For part B, you start with perchloric acid, which is the other reactant. You do the same thing. So but you just start with perchloric acid. And then you use that molar mass, that molar ratio, and then go to mass. Did that? Oh, you got a different limiting reagent? That's unfortunate. I could be wrong. I don't know. You can ask me afterwards and I'll use my calculator. Yeah. Okay, cool. But that's how you solve it. Who's next? Yes? Page 210 in the practice exam reader. What number? 14. This one right here? Okay. All right. So you know this ratio. Is that okay? That ratio is this number. Okay. You also know the carbon-12 number. Does anybody know what that number is? It's exactly 12. That was something we learned in chapter 2. All the atomic masses, isotopic masses, are based on carbon-12. And carbon-12 is exactly 12 grams. So if you know carbon-12 and you know the ratio, you just cross-multiply to find this number. Is that okay? So it's 12 times that number is the answer. Okay, that's it. Who's next? Way in the back.
Number 15 on
Fall 08 final. Pull up, let me flip over there. What number?
Number 15.
Oh my gosh. Of course you asked that one. This one. Right? Okay. Okay. This is a two-part problem. Do you want me to run through the whole thing or is it a specific question? The whole thing. Okay. So this is a two-part problem. One is to realize you have this reaction here is a redox reaction. The second part of the problem is to realize it's asking you a stoichiometry question. So what you have to do, we'll do this in a second, is to balance the redox reaction to get the molar ratios so that you can do the stoichiometry. Because you can't do stoichiometry without molar ratios. Does that make sense? And in this case, usually we've given you a non-redox. You just balance it quickly. In this case, we're giving you a redox. You have to balance the redox and then do the calculation associated with it. Okay, so that's the method. So, iron ores, a lot of this is ridiculous material. Contain ferric and ferrous ions, that's iron 2 and iron 3. Such an ore can be analyzed for its iron content by dissolving it in acidic solution. Okay, that's unhelpful for you also. For the most part, reducing it to iron. Reducing iron, here we go. This is the first important thing it says. Iron to ferrous. That's getting close to the most important thing. Okay, and then titrating it with potassium permanganate. That's that right there. Okay. The permanganate is reduced to manganese 2. Right there. Okay. And the ferrous ions, there's ferrous, is reduced to ferric. So really, the most important sentence starts right here. Permanganate. That sentence is the most important. That gets you to, so if you would have written down that sentence, you should have written down this. Okay? Then you have to balance this now with redox. Do you want to do that? It's up to you.
Sure.
Okay, so So first thing, you balance whatever is not oxygen or hydrogen, that's iron, and that's already balanced. Step 2, you balance the oxygen, there's none. Step 3, the hydrogen, there are none. Step 4, the charge, plus an electron. Next half reaction. Step 1, balance whatever is not oxygen or hydrogen, that's manganese, that's already balanced. Step 2, balance the oxygens with water, or water. Step 3, balance the hydrogens with H+. There's 8 on the right, so you need 8 H+ over here. In step 4, you balance the charge with electrons. And anybody, how many electrons do I have right there? 5. Why is that? Because 8 minus 5 minus 1 is 2. And that equals 2. Is that okay? Okay. So then, I've got to multiply the top reaction by 5 and add it. When you do that, you get that right there. I know it's kind of quick. I just want to get to a lot of people's questions if I can. Is that okay? Then it tells you that you have this molarity and this, milliliters and that molarity of the permanganate. And it wants you to calculate the percent mass of iron. So really, you need, in order to do that, you need the, the moles of iron. And ultimately the mass. So you need to find this. So what you would do is, so now we're entering into a separate problem, which is a titration problem. So this is a separate problem, but it's all one problem. And this is 1.621 times 10 to the minus 2 molarity. And we want to know, on the same side it's going to be iron. I guess I should write it out. Let me write it out. And there's some waters and stuff like that in here. Okay, so there's the reaction. We know this information about that one right there. We need to know information about that one because they care about the iron. So you go 41.56 times 1.621 times 10 to the minus 2 moles per liter. This is milliliters. You need to change the volume, liter for 1,000 milliliters. Now I've got moles of the permanganate. That's the MnO4. I'm going to do a molar ratio. There's 5 irons for every 1 permanganate. 5 irons for every 1 permanganate. And that, balancing the redox reaction gives me this number right here where my pen is. That's why I had to balance the redox reaction to get that number. This is now moles of iron 2+. I know that all my iron comes from the iron 2+ from the question. So this is really how many moles of iron I have total. I don't want moles, I want mass. So one more multiplication. The periodic table tells me there's 55.85 grams per mole of iron. And this will give me the mass of iron of 0.1881 grams. From here, I divide by the total, which is 0.3500 grams, and multiply by 100. Get mass percent. Crazy, I know, but that's how you solve it. Okay, cool. Next. Yes. I want to go to somebody new who hasn't asked a question yet. Yes.
Did you do number 25? Fall 08?
Fall 08, number 25. Fall 08, 25. Is this a xenon one? This one?
Yeah.
Okay. So it says, it tells you it's polar and wants you to draw the species out. Do you want me to draw it out with you? Like work it out with you? Yeah, okay. So xenon O2Cl2 2-. Okay, so xenon has to be in the center. It's giving you a list of things that are around it. Okay? We want the valence electrons. The valence electrons are 8 for xenon, 2 oxygen in column 6. There's 2 chlorines in column 7, and plus 2 for the minus 2 charge. So that is, oh, what is this? 26 and 10, 36? So that's 36. With the bonds, I've got 8 of 36 done so far. So let's continue now. 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. That's 32 of 36, giving octets to everything on the outside. I know xenon can break an octet, so I'm going to put the final 4 in the middle. What does not have a 0 formal charge? The oxygens have a formal charge of -1. Is that okay? Or do you want me to do that? Okay, so these are both -1, so you can fix that by removing these lone pairs. Well, you don't have to fix it. You can leave it like that. So you can either leave it like this, or you can attempt to fix it if you want and see what happens. Oh, what's the formal charge of the xenon in the center of this diagram, by the way?
Oh, yeah. I laid it across this one.
That was 0, right? Is that okay?
They do.
Okay, if you try to make the oxygens have a 0 formal charge, what happens to the xenon here? Its formal charge becomes -2. Which structure do we like better, the one on the right or left? Left, because we hate -2 charges. That's too big. So it's definitely this one, and that's what you'll see in the answer. Okay. Now, draw the diagram and state the geometry around the central atom. Okay. Well, how many groups? 6. So the electronic geometry is called octahedral, 2 lone pairs. The molecular geometry is called square planar. But this must be polar. I have drawn it non-polar because the oxygens are on opposite sides and the chlorines are on opposite sides. So really, if you wanted the real correct answer, I won't put, just for quickness, I'll just not draw the lone pairs for a moment. You've got to not draw these atoms opposite of each other. So you got to put the oxygens and the chlorines kind of close to each other. Put all the lone pairs back in, put the brackets back in because it's a 2- charge. Put the formal charges in, and you've got the correct structure. Is that okay?
It's okay if I have like the oxygens off each other.
No. The first diagram, we shouldn't report that one. The Lewis structure is correct, but the shape is not correct. And the reason is, they told us it was polar. And the top one is drawn non-polar if you say that's the shape. So it's the correct Lewis structure, but once I go to shape, square planar, I've drawn it square planar, but I didn't draw it polar. So really I have to draw it as I did on the bottom. Okay, good. Next.
That's if you want to show it's polar.
Well, awesome. All right, a last question. Yes. Buzzer beater right this second. Yes. I have to go home and go shopping at Forever 21. 23, you said? Winter 09, 23. Winter 09, 23. Fall, winter. Okay, I knew the last person would ask me a tough question. This one, the civil engineer question, is that right? Yeah. Okay. This is a dilution question. How do I know that? Because the mass percent is changing from 50% to 3%. We actually got this question from an actual civil engineer in Davis who sent it to us. We actually made it easier, and then this is what ended up on the final. So yeah, this is actually a true-to-life question. In the beginning, this H2O2 is 50% by mass. In the end, it's 3% by mass. We need 20 gallons of this. How many gallons do we need of this? So we need the volume here. We have the density of the 50% is 1.197 grams per milliliter, and the density of this one is 1.015 grams per milliliter. Okay? So I need to dilute this by adding water. Okay? So my how many gallons do I need to add? So really my answer is going to be the difference from 20 minus the initial volume. That's how much I'll add. So my initial volume must be less than 20 because it got diluted. All right, how do I solve this? Well, I'm going to use M1V1 equals M2V2. So far we're thinking, oh my gosh, how easy. Here's the rub. This density causes you cannot plug these percentages in here directly because these densities are not the same. Because of that, you need to convert this from percent mass to molarity. And that's kind of, for most people, the hard part of the problem. So, I'll do one of them, you can do the other one. Okay, so 50% per mass means this, 50 grams over 100 grams. That's what that means. Okay? So that's percent mass. And then this is grams of H2O2 on top and grams of solution on the bottom. Okay? Now, this here, if you look in the question, you'll see we specifically call this density a solution density. If you look in the question, do you see that? It says solution density at the end in parentheses. Okay, that means I have to multiply like this. Because this is the mass of solution. Is that okay? And then, for molarity, I need liters on the bottom. Okay? So milliliters are gone. And multiply, I need one more multiplication. So the bottom is set. I'm good with the bottom. I need to change the top to moles. How do I do that? The molar mass. The molar mass of this H2O2 is 34.01. So this will give me moles per liter. This one happens to be 17.6, I think. So what you would do is the same for the 3%. This would be 3 over 100 here, and this would be the 1.015 here. Everything else is the same. Is that okay? And then you can plug those numbers into M1 and M2. And the nice part is, what do you do with the volumes? You actually don't have to change it from gallons. You can, if you want. If you want, you can change it from gallons to liters, but you don't have to, because the gallons unit is consistent on both sides. So you can leave it in gallons, then you're going to get a gallons answer. It'll turn out to be, the initial was 1 gallon, the end is 20 gallons, so the difference is 19. You're adding 19 gallons. Okay. All right.